There is an easier problem called valid anagrams. We solved it like a few videos ago. Group anagrams is like the sequel. It's the sequel to valid anagrams, but it's kind of a trap. I'll tell you why it's a little bit of a trap. Given an array of strings, strs, plural s, group all anagrams together into sublists. Okay, you may return the output in any order. And as we know, an anagram is a string that contains the exact same characters as another string, but the order of the characters can be different. So whereas in is anagram, like the easy problem, this is a medium problem, by the way. The easy anagram problem is like between two strings, right? You got string A and then string B, and then you kind of like compare is A and B anagrams of each other. But now we kind of want to group them. We have a list of strings and we want to group them into sublists. Let's see what happens here. Hat is by itself because there are no other strings here. That is an anagram of hat. Cool. And act and cat are together because these are anagrams of each other. And then stop, pots, and tops are also one group, right? So we have tops, pots, and stop, an anagram. These two, anagram, this one alone. So how do we do that? Well, I don't know about you, but my first instinct when I saw this problem is like, hey, I've solved the is anagram question before. Why don't I reuse the code for that into this problem? Because this problem just seems to be an extension of that. Okay, let's try that. Let's see what happens if we do that. All right, let's have a look. Let's say I have a function is anagram. We have a function like this. The implementation is done. We have the function here, okay? We implement is anagram. Then what do? We would simply loop through every string and then test whether that string is an anagram of every other string, right? So if you have, let's say you're probably gonna do a double for loop. We have an I here, and then we go like, hey, I'm gonna check I with J. Are these two anagrams? Are these two anagrams? Are these two anagrams? Are these two anagrams? And so on and so forth. And once that's done, we increment I, and then we compare it with the rest of this. And then, you can just run through that whole process. At a high level, if you think about it, what happens to the time complexity of that? Okay, let's have a look at the time complexity of that. So we'll say the length of strs is n. And then like, I'll say the average length of each string. So this is the strs with an S is the plural, is the whole array. And then stir singular is just like the individual elements. Let's say the average length of a string is like m, okay? So the time complexity, if you do a double for loop, you're checking a string with every other string. How many strings are you checking? Well, you're checking n times n strings. And then for each check, you have to run the is anagram, which is, if you remember, is an O of what? I don't even remember, man. Fucking O of what? Okay, I just checked the is anagram time complexity and it's linear. We'll say n. Okay. So this is like, oh my lord, what even is this? We're looking at like, it's not even like a power of 2. This is like a power of 3 kind of, this is a power of 3 kind of solution. So it's bad. This is what I mean by it's kind of a trap where like, you think you can just reuse this, like, but it's not that easy. One solution that's significantly better is we go back to our friend sort. Yes, we know sort is a little bit on the expensive side, but sort is actually probably the most intuitive solution to understand. An intuitive solution that gives a pretty good answer. So let's start with that. So as we know, if we want to compare if two words are anagrams of each other, one of the easiest ways is to sort this string, and then we compare the sorted strings. We can apply that concept to the solution. Now, instead of comparing just two strings, I want the sorted string to act as a representation of the anagram subgroup. So what does that mean in practice? Let's have a look. Let's say I were to loop through the elements one by one. First element, act. I'm gonna sort act, okay? I'm gonna sort you. Well, luckily it's already in alphabetical order, right? So act becomes act, and then what I want to do is look, hey, is this sorted thingy in here or not? If it's in there, it means that there is already a subgroup that exists where all the elements in that subgroup are anagrams. of act. But since there is no such key in this dictionary, we have to create a new subgroup, right? No subgroup will take act, so we have to make our own one, okay? So we'll say that the key is act, and we have this one element in our subgroup, act. All right, let's go to pots. So pots, if I were to sort this, it becomes obst, right? So obst, I'm gonna look this up in our dictionary, see like, hey, do we have a key of obst? Well, no. So we need to create a new subgroup because there's no subgroup that matches this yet. All right, no problem. OPST. Now this is where it gets a little bit interesting. So I'm gonna sort tops. And that also becomes obst. And then we can use this to find, hey, do we have a subgroup that exists for this? Do we have an opt subgroup yet? Well, it turns out, hey, we do. So we can add this element in here. And then we repeat this process with cat, with stop, and lastly, we have hat, which becomes AHT. But sadly, there's no subgroup for AHT. So we have to make a new subgroup. That's all of the elements in stirs. Pretty good. By using this kind of structure where you have a key by having this kind of structure where you have the sorted string as the key, we can start comparing any new strings to check for if it belongs in the subgroup or not, which is pretty handy. And as you can see, it works perfectly. And at the end of it, since we want the output to be one giant list, and we also know that the order of the output does not matter, we can simply loop through the dictionary and grab all of these values and just like stick them together. And there you go. We have the solution. And let's have a look at the time and space complexity for this. Well, time complexity, we're looping through the entire list and we're going to process each element one by one. Okay, so we'll say that it's O of n, where n is going to be the length of stirs. Now, for each element that we process, we have to perform some sort of operation, right? So what are we doing in that operation? Step one, once we encounter a word or a string, we are going to sort the string. So let's say m is the average length of a string. Sorting a string would cost mlogm. And once we've sorted the string, we're going to do a dictionary lookup, which is O of 1. So I'm not going to bother writing that. And then once we've done the dictionary lookup, the next step is to append the string to the end of a subgroup if it exists. Otherwise, we have to create a new entry. And both of those operations are constant time, right? So effectively, the time complexity is n times m log m, which is much better than our n squared times m or whatever it was before. And the space complexity is, well, we need space to store this dictionary, right? So how many keys do we have here? Well, the keys are going to be equal to the number of anagrams, but in the worst case, let's just say O of n. The worst case would be we have as many subgroups as there are strings, and that's the solution. Now, this is not the final solution. If you were to check the hints, it would ask you whether you can achieve a time complexity of O of n m, which is better than this time complexity. Now, if you remember in our is_anagram solution, we know that although one solution is to compare the sorted versions with each other, the other solution was to use counter. And just as a quick refresher, this counter function returns a key value pair where it counts what letters are inside the string and how many times they appear. So in act, A would appear once, C appears once, and T appears once. This would be the counter, and then when you're comparing it to cat, let's say, cat would look like C is 1, A is 1, T is 1, and then these would be equal. Now, the problem is we can't just get rid of these keys and put like a hash map. This wouldn't work. Why wouldn't it work? Well, that's because hash maps are mutable. And because hash maps are mutable, they cannot be keys for a dictionary. That's because, let's have a look at a case where we try. This is going to be a little bit of a tangent, but I think this is important for your computer science understanding. Say we lived in a world where we are able to use mutable things as keys. So for example, I create an array 1, 2, 3. And as we know, lists or arrays in Python are mutable. We're able to get rid of this, we're able to add new elements, etc., etc. And if you know anything about hashing, if I hash 1, 2, 3, it's gonna give me something, right? It's gonna give me some value. Let's say that value is x. But if I change this value and then I end up hashing 1, 2, 3, 4, this is not going to give me x anymore. This is going to give me a completely different value here, right? So this is going to be a problem with dictionaries because dictionaries rely on hashing to work. So let's say again that we have R, which is 1, 2, 3, and I also have a dictionary, which is empty, no problem. So I'm going to insert this array into the dictionary, right? So I'm going to do dict R equals to 1, let's say. So internally, what's going to happen is we're going to take this array of 1, 2, 3, we're going to pass it through a hash function to get the hash, and then using that hash, that's going to be the internal key that Python will use when we perform dictionary operations. So let's say that hashing this 1, 2, 3 gave us the x, like we mentioned before. So we know that, okay, there's this value x, there's this hash x, and then which points to the key 1, 2, 3, and the value of 1, right? After this insertion, right? So this is kind of the simplified version of what's happening, of what it looks like in the backend. And then if I were to say modify R, and we're gonna say r.append 4, by running this, we know that it's going to be 1, 2, 3, 4. It's no longer 1, 2, 3, it's 1, 2, 3, 4, right? So when I want to do something like this, dict r plus equals 1, what's gonna happen? Well, this is actually two operations in one. First of all, we have to fetch the value r from our dictionary, right? So it goes off and it searches. Do we have a hash of 1, 2, 3, 4 in here? Do we have that? And we know we don't have that here because this x is from hashing 1, 2, 3 and not hashing 1, 2, 3, 4. So when we try to retrieve this, it's gonna error because this hash does not exist. This hash does not exist. So you can see that even just allowing mutable keys inside our dictionary will cause all sorts of bugs, right? Like imagine you're a developer and then you have to track down this like esoteric bug as to like why my dictionaries, like suddenly it can't find the key, you know? So to prevent that situation from happening altogether, languages don't allow mutable keys anymore. So how do we fix that? Well, instead of using the dictionary, which is a mutable type, why don't we try using a list? Well, we know lists are. Well, you might say, hold on, Chris. The example that you gave was using a list as an example of what doesn't work. So why are we using a list this time? Well, good question. Because if we use a list, we can convert the list into a tuple. So we can do all the operations we want on the list, and then we convert it into a tuple, and then we make that our key. That's the idea. So the key wouldn't be a list. A key would be a tuple that we converted from a list. And we know that tuples are immutable. So effectively, we're going to do some compute stuff to construct the list that we want. And then once we're happy with that, we set it in stone as a tuple, and then we make that our key. Okay, fine, sure. But the anagram solution actually uses a hash map, right? It doesn't use a list. So how would this work as a list? Okay, again, we're actually going to make use of this trait. Each string is only going to be made up of lowercase English characters. So that implies that at most there are 26 unique characters. So if we were to create a hash map, if we were to create a counters, this can only go up to 26, right? So it's a fixed size dictionary. So instead of using a dictionary, why don't we just use a fixed size array? The array is going to be 26 spaces long. It's going to look like this. 0, 1, 2, 3, blah, 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 and then 24, 25. There's 26 total slots here. So 0 is going to correspond to the letter A. 1 is going to correspond to the letter B, C, D, E, and so on and so forth. So this is, if you think about it, this is kind of a mapping. It's just a little bit abstracted away. Instead of saying like for act, we have A is 1 time, C is 1 time, T is 1 time. We're saying that in index 0, there is 1 occurrence of that. Index 2, there is 1 occurrence of that, and in index 14, there's 1 occurrence of it. So we know this represents A, this represents C, and this represents T. We're just reducing all the characters into indices in the list. Okay, so once we do that, effectively, it's the same thing. When we encounter a new word, we construct this mapping. And then once we have this mapping, we convert it into a tuple. And then once we have the tuple, we can use that as our key. So let's go through step by step just to really solidify how this algorithm works. So first, character act. We construct our this, turn that into a tuple. And then from that tuple, we will make that the key of the list. Like so. So pods, same thing. We're gonna get some kind of structure like this, and then we're gonna convert that list into a tuple. And then from that tuple, we're gonna check whether this tuple is in here. If it's not in here, then we create a subgroup. And as we know that this tuple is going to be different from this tuple. It's not gonna be the same because they're not anagrams. So we have to make a new subgroup. The ones are gonna be in here somewhere. And then we run through tops, create the list, convert it to a tuple, then we do a lookup, and we know that it should match this. And because it matches, it's gonna be inserted. And then now we just repeat the process for the rest of it. And we should end up with the same result as our previous sort solution. Now that we have all this, it's pretty simple. We just grab all of the values, this, and then we just join them together into one big list. So that's the plan. Let's get to coding. So first of all, we have to write a for loop, right? For, do we care about the index? Not particularly, so I'll just say for stir in state. Oh, also, I need the results array that we're going to use to contain all the subgroups at the end. And next, I need a dictionary. So I'm going to create a dictionary called groups, which is just empty for now. Okay. So first of all, we encounter a string. Bam. We encounter act. What do? First thing we do is we need to convert this into the list structure, the list mapping that we mentioned earlier. So first of all, we need to create that list, obviously, and it's size 26. So let's make it key is equal to 0 times 26. And as we know, this key is going to store the representation of all the lowercase English characters from 0 to 26, where 0 is lowercase a, and index of 25 is going to be lowercase z. So this is going to be indexes 0, 25, inclusive, right? Next up, we have to loop through each character inside the string, and we have to start mapping them into this, okay? For C in stir, I have to find which index corresponds to this specific character. To do that, I'm gonna have to use the ord function, ord C. So what does ord do? So ord stands for ordinal, which is the integer representation of any character. So we're gonna run the ord function on this specific character, which will give us an integer, right? And if you check, for the letter of lowercase a, the decimal representation of this is going to be 97, and the letter b corresponds to the integer 98, c 99, d 100, etc., all the way to z. If our string is act, and we're taking the first character, which is a, this ord c is actually going to be ord a, right? So this is going to give us the value of 97, as we've seen in the table before. So if we minus this with the ord of the letter a, then this is going to give us the index 0. And for letter C, if we refer back to the table, it's 99. And it'll be 99 minus this, which is 97, which will give us the index 2 in our list here. So that's going to be the operation we perform. Once we have the index, we're going to increment the value of that index by 1. And then we repeat this for every character inside act. So the index of A gets +1, the index of C gets +1, and the index of T gets +1. And our key is all filled up now. Remember, we have to convert this list into a tuple before we can use it as a key proper inside our groups dictionary. So we can just say that the key is equal to the tuple key. And from here on, it's just simple logic. If key not in groups, then we have to create a new subgroup. Groups key is equal to is going to be a new array with the string. Otherwise, if the key does exist in groups, means there is a matching subgroup. It means we can simply append it to groups key, which will be a list dot append the string. Now that that's done, we're simply going to loop through all the values of groups and then add them to the result to make one giant list of all the subgroups. So we're going to say for subgroup in groups.values. So we don't care about the key anymore, we're only grabbing the value. We're going to say result.append subgroup. And there you have it. Let's see if this works. And it works. Accepted, passed all test cases, and that's the solution. Okay, bye.